Welcome, everybody. Wow, that's a terrible, terrible beginning, but how's it going?
Are we starting right now?
Yeah, well, I mean, officially starting. Oh, wait, I forgot to press play. That totally ruined it. Oh, and I ruined it in the other video too. Forgot about that. Anyway, okay, so
All right, you will get better at making intros. I sincerely hope.
yeah, really. Okay,
We're gonna
so
have like 3D animated intro soon, like one of those YouTube stars.
Yeah.
It's time for some game theory.
Pew, pew.
nice. Perfect.
All right, homeboys. I can can we make this into a whiteboard screen
Yeah,
where we have fans?
if
And
you could
that.
share screen. Nice whiteboard.
Yeah, cool. Because like the impression that I got was that I have been the person reading the content, and you other guys are expecting me to explain.
I would love
Where
that.
did you get that idea?
I don't know, but I mean, this chapter is not that difficult. It's pretty straightforward, so you should be happy that you didn't read it, and I'm sad that I didn't read it. But we're doing two-person games, and they're no longer necessarily non-zero, or they're not zero-sum games. So we have two-player non-zero-sum games, and we represent them by two matrices, like this, where here are all the entries and rewards for player one, and here are all the words for player two. Okay, so then you do some linear algebra to figure out what the best strategy is, and you do some analysis. And so what you want to do specifically, the type of analysis that you want to do, is that if you're player one, you want to calculate the expected value of your A matrix, of course, as we always do, which will be this stuff. Bam, bam. And so
Is Y in this case from
player
the
two, excuse me?
is Y selected from the A matrix or the B matrix?
None of these are, X and Y are not from the matrix. X and Y are a particular strategy for player one and player two.
Oh,
Right, it's a
yeah.
vector, right?
Yeah, so if we have an n times n matrix, then A and B, this is an A and this is a B, good. Then X is going to be in what they call like this probability space, and Y is going to be in this probability space, and it's basically just like a particular X is going to consist of a bunch of variables that all add up to one, and there are many of them.
You write very legibly and quickly. Have you got like a drawing, like this drawing pad, or
No, I'm just
practice with your mouse?
I'm just doing it with my mouse, and I'm doing it like very as quickly as I can.
Yeah,
But
playing League of Legends or something.
I was playing a bit of Dota before this, so maybe I
Warmed up.
Yeah.
Okay.
So what we want to do specifically is like, as player one, because we're player one, we're the best. We want to figure out our best response to a particular strategy chosen by player two.
Okay.
And so that is going to be called BR of Y. PR, like we do a little subscript 1. So given a particular strategy, we want to, of course, maximize this basically. Do I have different colors? Wow. Max this.
Mhm.
But
With I being variable.
with X shifting. Actually, to write this properly,
Oh yeah, right. Yeah.
the best response is a set valued function. So I'm going to write down exactly what it looks like. PR1 of Y consists of nice.
Holy wow, this is impressive.
all of the X and Y in this probability space that we know. I changed to subscript because that's just as good. That satisfy that E of X and Y is equal to, this is over matrix 1. If you maximize P in this probability space, the response like so. Okay.
Mhm.
So the best response for player 1, given a particular strategy of player 2, are all of the strategies for both player 1 and 2 that are actually the best in this scenario.
Why is it the strategy of player 2? Because we already know that.
No, we don't know it, but it's just given a particular strategy of player 2, this is our response, our best response to it.
Okay.
So this does not yet give us our Nash equilibrium.
Yeah.
Only in the case where, well, I'm going to get to that, where
They're the same.
yeah, so for all X and Y that are in both, let's see how I'm going to write this. Anyway, I'll do Nash's theorem, and then maybe I'll get back to this later.
Now I got it.
Okay, so what we're doing is that we're defining a function phi in order to get to Nash theorem, which is like the central result of this section, saying that every game has a Nash equilibrium in mixed strategies. And obviously this will work for any finite game for 2 players. I think it will work also for arbitrary many players, but they didn't go over that in the book yet. But anyway, we're gonna define a function phi, which is going to be a set valued function. So
what is a set valued function?
It's a function that outputs a set. So like if we look at this function, let me draw BR here. It takes a single vector as input, but it gives it gives a subspace of Sn cross Sm as output and not a point of that space.
So and that's essentially that's all of the or all of the choices, is that the right word?
All of the strategies that are optimal for responding to Y.
Yeah.
Yeah. Okay, so somebody else is writing something there. That's nice. Oh yeah, this can be a good thing. SM actually, but okay.
Oh yeah, you're right. Sorry.
Yeah, to the power set of Sn cross Sm. That's exactly right. And so similarly, function phi is also going to be defined in that way. It's going to take inputs in our strategy space and outputs a set of strategies. And it's pretty easily defined as just for x and y, it's going to give us, who can guess?
For all, it's going to be like y star.
Oh,
okay.
right. BR.
Yes.
Yeah.
Yeah, the best
Yeah.
response.
For x, y star.
For y, play one. And like, since I defined this like this, it's actually going to be, let's see, is it going to be the union? Should be the union, I think. Yeah. I didn't define BR2, but I think you guys can figure it out.
Yeah.
Yeah, so let me see, just see if I'm correct. I think I am. Proof. Da-da, da-da. Yeah, they say cross, but I don't really like that.
Cross doesn't make sense. At least not
No,
with
it
that
doesn't
type.
actually. Yeah.
Why doesn't it make sense?
Because this is going to output a set, and if you take like you can take two. Because that's in that case you wouldn't get the power set back. You would just get the same setback. So instead of getting the P of Sn times Sm, you would just get Sn times Sm, because you get those two sets in, and that's already the power. So the power set. No, sorry. So the Cartesian product is what you use to create tuples, which is what you already get in. But here we aren't creating a, apparently we don't want a tuple out. We want a set of tuples.
Yeah, but actually, I think I should be a little bit more careful just in how I describe the best response, because it might just be all of the x's that satisfy that. I think it might be, actually, because then it makes sense with the cross product there. So let me just see quickly. Taliban. Taliban.
That's my jam.
All right, whatever. Let's assume I'm right. It's gonna work.
That's a nice assumption. Like when you do proof stuff, assume that I'm correct.
Yeah. So, yeah. And now we're gonna change this to the cross. Okay. And then everything is fine. Okay. So now.
So you're now adjusting best response.
Yeah, so let's say that the best response only consists of all of these strategies for player one, and not the set of strategies for both of them. I mean, it wouldn't have added anything anyway, like if I like save myself here from this terrible mistake that I made, it's actually the case that for a particular y, the space of x's crossed with a y is going to be isomorphic to the space of x, because y is going to be a particular point that is just added, and it doesn't like give us any extra information, but whatever, let's get into that. So anyway, the point is here that if we have the particular scenario where our input to this function phi is contained in the output of the function phi, then we have a Nash equilibrium, because then both players are playing their best strategy given the other player's strategy. Does that make sense?
Yep. But I'm not sure if it would have made sense if I hadn't understood this previously.
So if x, let's call them something else here. Let's call them like x star. If x star is contained in the output of the best response for player y's response to player 1 playing the strategy x star.
And that has to be a best response of y, or is that, and is y, oh, okay, is y the matrix of, is it like all strategies, sorry? Is it a set of strategies?
It's a strategy.
No.
Y is a strategy. So then is it necessary for you to say that it's only for y when y is it for all y?
For any x and y that satisfies this condition, that particular x and y is a Nash equilibrium.
Okay.
Because
this condition, right?
Yeah.
But would you say that the x? So that, I mean, I guess that is a Nash equilibrium, but the thing that I'm thinking is that you have an x, which is a strategy, and that for all of y's strategies, that strategy should be a best response, or should be like or is there a best response of x and a best response of y?
So it's
maybe I don't understand the output of phi. That's probably what.
Okay, so the output of phi is going to be the optimal strategies for player 1, given that player 2 plays the strategy y, and the output, the second output, like the second half of the output, is going to be the optimal strategy for player 2, given that player 1 plays strategy x. And now, sorry, you go ahead.
So since we have a cross here, this will output a tuple. Oh wait, right. Since we have, never mind. Continue, Martin. You already have the tuple from before. Never mind.
Yeah. And so if there is no better response for player 2, I mean, if y star is just as good of a response to player 1 playing the strategy x star, and player 1's response to player 2 playing y star, if player 2's best response to player 2 playing y star is x star, then no player can benefit from changing their strategy, and so that is a Nash equilibrium.
Yes, and that's why I'm confused why you have one strategy as an input to the phi function, the Nash equilibrium function. You have one strategy for X and one strategy for Y, or player one, player two. And so how would you know that there aren't better strategies for either one of those? Like, is it a set of all the strategies, or are you going to say, like, give it one strategy for X and then for every strategy Y, like the best response holds?
So if there was a better strategy, then for a particular X and Y, let's call them this, then we would have that it's not contained in the output of this, because that means that when player one is playing X, what do you call it? X dot X.
X prime.
X prime. Thank you. When player one is playing X prime, then player two can respond with a strategy.
Oh,
which is better than playing Y prime.
Yes. Okay.
So Y prime is not in the set. Maybe the best response for player two when player X is playing X prime is not necessarily Y prime, and so they can benefit from changing strategy.
Yeah, and should that be Y prime, or should be Y? Okay, that should be Y prime. Okay, and that's because the best response for Y is the set of X, and it goes through all of it like maxes out the expected return for all of Y. I mean, it's good. I mean, best response 1 is for
player one's best strategy when player two is playing the strategy Y.
Yeah. Exactly. Okay, so it goes through all of the different strategies. Okay. Yeah.
Well, it for a particular input strategy for player two, then it outputs a set of all of the optimal responses for player one to that.
Yeah.
So it outputs a set, but it takes a single value as input.
Yes, exactly. Okay, that makes sense. Yeah, that makes sense. And that's because the thing that I was confused about is I was looking for where all of the set of strategies was getting compared, was getting maximized, the expected value against all strategies. And I didn't realize that was inside the best response 1 and the best response 2. And so because we're comparing against the set of all strategies in the best response 1 and the best response 2, then the output of any single X and Y strategy given to exactly will return only the best responses for both of the or the Nash equilibrium, I should say.
So I mean, it's in the maximization. One could say that you consider all possible responses that X could do and take the best of them.
Yeah.
But we always only consider the single inputs in the best response function.
Yeah, that makes sense.
Yeah, and so the corresponding looks like this. P.
Yeah.
And now the definition of phi looks much more reasonable as well.
Yeah,
exactly.
Yeah. So so the set of Nash equilibria, if you will, are going to be for a given game maybe is going to be the set of all points that satisfy this.
Yeah, cool.
And now, wow, somebody's calling me. Hang on, let me just not answer that.
Martin always gets a call in every meeting. Such a popular dude, my god.
So now the existence of Nash equilibrium is given from a fixed point theorem, which basically says that if you have a set valued function that satisfy certain conditions, such as that it's compact, which which phi is, because the set of all strategies, I mean, it's bounded because we only consider strategies with values ranging from 0 to 1, and we have a finite dimensional space and typical Euclidean geometry on it, so it's bounded and it's closed and everything is nice, and it should satisfy some other properties also, that it is that phi satisfies it basically. Then there's always a fixed point like this. There will always be points in this space such that the input is contained in the output of phi. And they prove this with Kakutani's fixed point theorem, if you want to look that up. Kakutani. It's a pretty nice theorem. It's a generalization of Brouwer's fixed point theorem that I think they used in the other game theory book.
Yeah. Is this easier or harder to digest?
I don't know if did you find Brouwer's fixed point theorem hard?
I actually just skimmed it, so I don't know.
I think it's
but it seemed very detailed in a not so nice way.
Yeah, because they want to do it in the general case, like for any topological space, and then you have to define what it means for an arbitrary topological space to be compact, and so on, and then it needs to be pretty detailed if you want to make it general enough. But I think the Vsauce video on fixed point theorems is approachable for people.
Yeah, I watched that.
Yeah. So that's nice.
Could you link to that video?
Well, I linked to it before.
Oh.
I can link to it again.
Apologies, I must not have.
Fixed point Vsauce, here we go. And so it's one of the things that you use to prove the hairy ball theorem, which says that if you try to comb a ball, like if you imagine you have a ball and it's very hairy, there's always going to be a part of the ball that you can't really comb, like where everything is diverging.
I love the imagery.
Whereas if you were to have a torus, then you can't comb it. So that's nice. Cool. So that's the main result of this section, Nash's equilibrium, or Nash's theorem.
Awesome, guys.
Yep.
Yo.
I gotta go.
Okay.
Caught up though. Finished chapter 1. Didn't have any questions. I think
Cool.
I've rubbed enough. This seems very familiar from the stuff I was reading at the end of chapter 1. So hopefully it doesn't take me too long to get through chapter 2 in this. What is this section? AKA, what is the current state of the art in Game Theory Study Group?
Chapter 3.
Yeah.
What? Like section 1, section 2? Both of them?
No idea.
I think I read through all of chapter 3.
Oh, wow. All right.
So that was chapter 3, like in a nutshell.
Cool. I will definitely rewatch this, and I will hightail it through chapter 3.
That was so good. Thank you, Martin. Wow.
Thank you, Mark.
Yeah, you're welcome.
Always a pleasure. I'll see y'all later.
All right.
Bye.
See ya. Okay, so that was so those are the definitions of Nash equilibrium for 2-player games with arbitrary size matrices and non zero sum values. Cool.
Yeah.
And so I'm sure they went over probably like implementations of how to actually like, you know, put it together. I mean, like find these with, but I mean, would you say that it's probably like, if you know the definition, that, and you can just use an implementation of the,
I'm not sure what Martin is going to say, but I don't think so, because this doesn't tell us at all how to find it except for brute force. It doesn't. It just tells us like what an equilibrium has to fight to be an equilibrium.
Yeah, one thing that may actually be useful is they gave a 3-step thing. And step 1 was determine if it has a pure strategy Nash equilibrium, I think.
Mm-hmm.
Is that what it was? Oh, I'm sorry for drawing on your screen.
Oh, did I just erase what you were drawing?
It's okay. I think I don't remember exactly what it was. I wrote it down. I wrote down the 3 steps because I actually did go through some of chapter 3, but I didn't get through the whole thing. But that was
just said that so that Martin would explain everything to you.
Yeah. Okay, I figured it out. So 1 is there a Nash equilibrium for pure strategies? And then 2, is there a Nash equilibrium for mixed strategies?
Yeah.
And then 3, how do we compute these? Those were the 3 steps that they gave in the very beginning of the chapter. And so the pure strategy Nash equilibrium by hand is like easy if it's a small set. You can just, they gave us like a simple, like, you know, drawing method for finding the pure strategy Nash. And then I don't remember how they said how you would determine whether or not there's a Nash equilibrium for mixed strategies. Like, more than one. I wrote. Yeah, it seems weird because every finite game has this Nash equilibrium for mixed strategies.
Yeah.
So that seems strange.
I can work through an example. It's example 3.9 that they give.
Oh, cool.
Where they talk about what they call page 136.
Thanks.
They talk about the calculus method, which I think is kind of funny. But like if we, so it's basically just like considering again, like we had a maximization in the best response, right? And so of course, if we want to find the maximum, we're gonna take the derivative and see when it's 0. So in the case where it's a simple 2x2 matrix, then what we're gonna have is a scenario like this. And maybe I'll actually do the general case because it's more informative, maybe. But so, I mean, this is going to give us the expected payoff for player 1 if they play a strategy, which is x and 1 minus x. If player 2 plays a strategy y and 1 minus y. And so to figure out our best strategy in this scenario, we're just going to take the derivative, of course. Let's just call this E1 with respect to x. And this is going to be the derivative of, maybe I can even do this in the general. Yeah, let's do it generally first. So we have entries A11, A12, and then A21, A22. Okay, and so if we were to have a matrix here, we do x times 2 minus 1 plus 1 minus, or actually not like that. Oh god, I get to show how horrible I think linear algebra is.
It is horrible, isn't it?
It is horrible.
I would much rather like use category theory.
Yeah, I know. Oh, I was gonna do it in general
So
case.
why is linear algebra horrible?
Because it's boring. I mean, you just like multiply matrices, and the procedures are super simple. You just need to think about computation, and that is never
Yeah,
fun.
sure. I can see that.
This is 2, 1, and then here you have 1, 2. Oh, it's gonna be plus there, and 2, 2. And then you're gonna multiply this with your favorite matrix over here. And like you need to always remember like which way matrix multiplication works.
Yeah.
No.
Because you
Yeah.
just, I know.
I think we actually put the Okay, so you do have the t there on the y vector, so that's good. But the x vector should also have a t.
Yeah, it should. I think so too. Yeah, I mean, they should both be row vectors. And then, did I still write the correct thing here? Yes, I think so. I think this should be, let's also put a T here. Okay, super. And now we're doing x times A11 times y plus x times the same thing, right?
Oh, right. Yeah. X times the same thing times 1 minus I.
No, I think like this.
Wait, is it?
I'm not
Maybe
sure.
it is.
Anyway, we don't have to care about the matrix multiplication. I mean, it's going to work out if you do it carefully
Do it
enough.
right, yeah.
Yeah. But I'm just going to clear that and write out what happens if we just do the computation right, because then we can actually take the derivative of it, and that's what we want to do.
Yeah.
So for those particular matrices that I gave you, the ones that are also on page 139 there, you're going to get 2x minus 1 minus x, I believe, y, and then what is it? Minus x plus 1 minus x. Cool. And now if we organize this a little bit, we're gonna get x, y, minus y, minus x, minus xy, plus 1, minus y, plus minus x, plus xy. All right, that's awfully nice. Cancel the shit out of nothing. Okay, good. And then we get 1 minus 2y minus x. And let's do this. Okay. And then if we just take the derivative of this with respect to x, we're going to get 1 minus y.
Cool.
But that's not perfectly right. Should be a 2x here.
So really cancel nothing.
And there should also be a plus xy here. I don't know what I was doing here. Where's that minus x from? That shouldn't be there, actually. Oh, there's the, okay. Now it's starting to look better. My plus 1, okay. Crazy. Where were you guys when I was doing this? Get away with everything.
I was
right.
I was actually looking at an apartment that I might be renting.
Oh, nice.
Like not
for you,
not
Jack.
physically, just on pictures.
I was watching, but I was just like mesmerized by your algebra. So
I trust you way too much.
Yeah.
Exactly.
Yeah. Just
Okay, let's just let him finish, and I will go back to the screen. And then I couldn't figure out how you got from the equation. Okay,
he must have done something fancy.
I promise to check you more in the future.
nice. Good. I think what I wrote was pretty good. This should be a plus. Okay, and now stuff is actually right. I think so. Good. So I have a lot of xy's. How many? 5.
Like 4.
Nice.
Oh, yeah, 5. One at the end.
Our help might not be as useful as thought.
Good. Cool. So this is gonna give us.
Wait, what happened to?
I don't care about those.
Okay.
Because they're just constants.
Yeah, sure. Yeah.
So this is actually the correct answer.
Are you just asserting that, or is it
This I checked with the book.
nice?
Yeah, so I mean, we just take this whole thing and we take the derivative with respect to x,
Yeah.
and then we get, and then we set that to 0, and then we get this thing, and then we solve for y. And so what have we actually done now? We have figured out what the best response. No, we haven't. We have figured out
The weight?
the
Probability that they would choose that strategy. Which one would it be?
We figured out the strategy that player 2 can choose that maximizes the expected payoff.
for player 1 though.
Yeah.
Do we derivative in terms of y? That sounds weird. Yeah.
Yeah, so this gives us a Nash equilibrium, and I don't think that I can explain why, because it doesn't seem like we get strategy for x, like we determine player 2 strategy when we calculate what player 1 should be doing.
Yeah, exactly.
Well, we can do the
It's really
same
weird.
for player 2, right? And then we
Yeah,
can,
sure. But what like why if we do the reverse, we're just gonna figure out how player 1 maximizes player 2's payoff, which is not exactly what we want, or at least not intuitively. So I kind of agree with Martin that I don't understand how this gives us a Nash equilibrium.
It gives us 3/5. But the thing here, I think, was that our best strategy for player 1 is independent of our own strategy, which is strange. Our best response, or the maximum of our function, is reached when player 2 does this, regardless of what we do.
Yeah, sure.
By our, you mean player 1 or player 2?
Yeah, player 1.
So when player 2 does that, then player 1's
Strategy is optimal. It seems like they're helping each other an awful lot, though.
Oh man. So I have to go relatively soon.
Yeah, I was about to say the same.
Yeah.
But we
So
got
we're-
close. This is cooperative game theory. Welcome.
This is the method that one uses,
Yeah.
and I thought it was pretty intuitive up until this. Because then you're just maximizing a function, but it's just strange that the function reaches this maximum when player 2 does something.
Yeah. But I'll go over the method myself, and hopefully I will be able to make sense of it as well.
Yeah, it should be.
At least when reading it, we'll see how it goes when I try to apply it.
Cool. Awesome. Sounds good.
So are we doing the whole of chapter 4?
I mean,
next week, or
what do you think,
Like-
Jack, before I say anything?
Like, given that neither of us have completed chapter 3, maybe that's a bit optimistic. And like, honestly, I have a bit I need to prioritize because I am probably gonna start working for DAPUB and have to set up my own company and so on to be able to invoice them. So I ended up, and I'm studying this in linear logic, and I tend to prioritize linear logic when I have to prioritize, and I suspect that I will have to prioritize next week as well. So we could talk about chapter 4, but I don't know how much time I will actually have to do.
Sounds good. That's exciting that you're working with DAPUB.
Yeah, I agree.
That's super cool. That's the move.
It's actually not finished yet, so maybe I shouldn't talk too much, but it seems more or less like I have it.
Okay, cool. Well, I'll just publish this on YouTube and then link it for people.
Perfect. Yeah, I see that the recording sign up there.
just FYI.
Yeah, but no worries. I don't think they care. I don't.
Yeah. One of our viewers is going to notify them just to make sure.
Yeah.
Anyway, okay, cool. Well, I'll go over chapter 4 at least as much as I can. I'm really excited to learn about all the concepts and have a relatively good understanding of all the concepts. So I'm happy to go fast. And I also that was an awesome presentation, Martin.
Thanks.
It was.
Cool. Well,
thank you.
Awesome. Well, have a wonderful couple days, and I guess I'll see you for linear logic on Tuesday.
Yeah,
definitely.
All right,
Yeah.
Viewers, catch us then because I won't mess up recording for the 3rd time in a row for linear
All right.
logic.
Cool.
All right. See you guys.
Hey, folks.
See ya.